Welcome back to this unit on non-spherical particles. In this part, I would like to work through a calculation example for the moment of inertia. First, let us make clear that in most cases we will prefer a numerical solution. The reason for this is that we would like to have an as general as possible solution strategy. So let us briefly look at such a strategy, which is the Monte Carlo integration. In a Monte Carlo integration, we choose a bounding box that surrounds our non-spherical particle first. You see this here beautifully illustrated in the image provided by Eva Siegmann. You see here red dots, some of which are filled with a white color and some of which are filled with a red color. Obviously, the red colored dots correspond to the mass points that are inside the non-spherical particle. So what we do now with a Monte Carlo integration, we approximate this integral here for the moment of inertia relative to an axis E1 by a summation over these tracer particles with mass delta m that are inside the non-spherical particle multiplied by this normal distance to the axis to the power of 2. So this is very easily applied to any axis and any body, and especially for the multisphere approximations, this is a relatively simple programming exercise. The reason for that is that in the case of multispheres, we know the centers and the radii of each of the composite spheres. We then just have to check whether these tracer particles are inside one of the composite spheres or not, and that's it. Let us now look at an analytical solution. This is needed for verification purposes, for example. We need to also pick a concrete example. And here we have picked wooden cylindrical rods or dowels that are heavily used in the furniture industry. Let us assume that the length of these dowels is 4 times the radius of the dowel and that the dowels have a mass of mw. We will now calculate this moment of inertia analytically for several approaches. The first one is a simplified multisphere approach. Here we assume that we have 2 point masses at a fixed distance 2r interacting with other rods via these spheres of radius r. So we have a strong assumption that we use a very rough multisphere approach, and in addition we assume that the mass is concentrated at the centers of these spheres. You will see that this makes a big difference if we calculate the moment of inertia. The second approach is to use the classical multisphere approach, where we have 2 spheres, and we will consider that each of these 2 spheres has a finite moment of inertia. And the third approach is, and this is maybe the most realistic approach, the spherocylinder approach, and you see it depicted here. The only thing that we cannot do is we can of course not take into account the sharp edges at the end of our dowels, but this is it. Let us first think about what do we expect for the dowels. Let us calculate a reference moment of inertia. For such simple geometric shapes, the moment of inertia is known from an analytical solution of its definition. For example, for a cylindrical reference particle with lengths 4r and radius r, we find in any textbook that the moment of inertia with respect to this axis here is nothing else as the mass of the particle multiplied by this term here. So you see that both the radius and the length of the cylinder matter. So if we evaluate this equation for our situation, we arrive at this solution for the reference moment of inertia. To round up this slide, we can summarize and say that this reference moment of inertia is approximately 1.58 times the mass of the particle times the radius squared of this cylinder. Let us now move on to the next case, the simplified multisphere case. The moment of inertia of point masses can be easily calculated based on their position relative to the axis. For this case here, we see that each of our point masses has a mass of mw divided by 2. It's half of the total mass of the particle. The moment of inertia of each of the point masses is simply the mass of it multiplied by the radial distance to the axis, and this is in our case r. If we now express this in terms of the total mass, we arrive at this equation. So we see that this is much smaller than our 1.58 times mass r squared. It's just 1 times the mass r squared. So obviously the simplified multisphere assumption is not very realistic. The next assumption that we have outlined before is the multisphere approach. Here we have to consider the so-called parallel axis theorem. This is a very important theorem when calculating the moment of inertia. It says that the moment of inertia with respect to any distance of the center of mass to the axis, and this distance is called here d, is simply the moment of inertia about the center of mass plus the mass of the body multiplied by the distance squared. So we note already that this second term here is exactly the same as on the previous approach number A. So the only thing we have to do is we have to add this center of mass moment of inertia, which for a sphere is nothing else as 2 over 5 multiplied by the mass of the particle multiplied by r squared. So if we think about it, we find for the single sphere with this mass, we find that its moment of inertia with respect to the center of mass is nothing else as 1/2 multiplied by 2 over 5 multiplied by this term here. For a single sphere, we have already identified this second term here, and now we just have to add things up, and what you see is that you arrive at 7 over 5 mw r squared, which is 1.4. So this gets much closer to our reference of 1.58, but still we are 12% off. Also please note that we cannot improve this calculation by considering more than 2 spheres. And the reason is that the spheres in this simple analysis cannot overlap. Let us transition now to the last approach, the spherocylinder approach. You will see that this derivation is more involved. First, of course, we have to separate the cylindrical part from the 2 hemispherical parts. Of course, we have 2 hemispherical parts and only 1 cylindrical part. Next, we must note that the split of masses between the cylindrical part and the hemispherical part is not equal. If you go through the definition of the volume of a cylinder and the volume of a hemisphere, you will find these expressions here for the mass of cylinder and hemisphere. The total mass of the particle is then calculated via this expression, and we arrive at this important result. If you do the math, you will see that 60% of the mass goes into the cylinder for our situation and 20% into one of the hemispheres. We now solve the first part of the problem, namely the moment of inertia of the cylindrical part. You have seen this expression already. Please note that now we have to consider the mass of the cylinder and of course the shorter length of the cylinder, which is only 2r. If we put these numbers in and if we then replace the mass of the cylinder by the respective part of the total mass, we arrive at this important expression. Please note that when going from this equation to this equation, we have used this relationship here. The final and hardest part is probably to calculate the moment of inertia of the hemispherical part. Therefore, we have to consider that the center of mass of these hemispheres is not located here at the end of the cylinder, but at a certain distance from this point. This distance is 3/8 times the radius of the hemisphere. We now use again the parallel axis theorem to arrive at this expression here. This is of course the moment of inertia of a hemisphere, which you can find in this reference, for example. If we then again put in the numbers from our example and replace the mass of the hemisphere with the fraction of the mass of the full wooden cylindrical rod, we arrive at this sub-result here. Please note again that we have simplified this ratio here with this ratio. We can now finalize our example by simply adding things up. We add to the moment of inertia of the cylindrical part 2 times that of the hemisphere. We have seen these results before already, and we arrive at approximately 1.21 times the mass of the wooden stick multiplied with r squared. You can also consult this reference here, where the derivation is made for a more general situation. Note the relative difference of this approximation is minus 23.6% to our reference. This was it for this part. I hope you enjoyed it. See you next time.